Hi, my name is Fabien Duflon from Deterministic, and I'll be presenting efficient deterministic leader election for programmable matter. This is joint work with Shai Kuten, also from Deterministic, and William Moses Jr. from the University of Houston. The notion of programmable matter was introduced by Toffoli and Magnus back in 1993. It refers to large systems of smart cooperating particles. These particles are small and hence limited in memory, computation, communication, and movement. The images to the right show what such particles look like in current prototypes. The first natural application of programmable matter is forming objects on demand. A concrete example of that is bridge building. A slightly more complex example is electronic clay for computer-aided design. More precisely, the particles form a shape that physically reflects on computer 3D design, allowing for both better visualization but also direct changes by physically moving particles. Second, particles can be used to form smart paint layers, which have the additional ability to monitor and repair structural integrity. Third, very small particles could be used to perform surgeries inside your body. In this work, we consider a formal computational model for programmable matter called the geometric amoebot model. It was introduced by Dirac-Chandé, Richa, Dolev, Scheidler, Miraz-Hoffman in 2014. This model first assumes we have a planar triangular grid G, which you can see in the center image. We also have n particles. Remember, these are the mobile computational agents. These particles occupy nodes in the grid. More precisely, a particle occupies either one node or two adjacent nodes. If the particle occupies a single node, then it is said to be contracted. Otherwise, it is said to be expanded. Particles can move along the edges of the grid. A contracted particle can expand into any of its adjacent empty nodes, as you can see here. An expanded particle can contract into any of its two occupied nodes. Once again, you can see this operation here. We consider an asynchronous distributed system. This asynchronicity is modeled by an asynchronous scheduler. The scheduler is sequential. A single particle is activated at any time. This is called the strong scheduler in the amoebot literature. Additionally, the scheduler is fair. And note that in an asynchronous round, every particle is activated at least once. An activated particle reads the memories of its neighbors, then writes into their memories, and finally chooses to move or do nothing. Now that we have defined our computational model, let us introduce the leader election problem. This well-known distributed computing problem is especially important in the amoebot model. Indeed, most known leader election algorithms assume a leader is initially given. We define two variants of the leader election problem. For both, initially the subgraph induced by the occupied nodes, here colored in black, is connected. So this subgraph is called the shape of the particle system and can also have holes. And holes are the connected sets of empty nodes that are initially here enclosed by the occupied nodes. We also allow the particle system to disconnect during the algorithm. By that, we mean that the subgraph induced by the occupied nodes is allowed to be disconnected during the algorithm. I do want to point out that this assumption is uncommon. In the disconnecting leader election problem, the algorithm should terminate with one leader particle. However, the algorithm can terminate with a disconnected particle system. In the connected leader election problem, the algorithm should terminate with one leader particle as well as a connected particle system. This additional condition is very important since other algorithms that use leader election as a building block generally assume that the particle system is initially connected. In this work, we provide a deterministic disconnecting leader election algorithm with a linear in diameter runtime. Since this algorithm may leave the particle system disconnected, we also provide a deterministic reconnecting algorithm. This algorithm also has a linear runtime in the diameter. By composing these two results, we obtain the first deterministic linear time leader election algorithm for initial shapes with holes. This result closes the gap between deterministic algorithms and randomized algorithms. The rest of our presentation follows this outline. First, we will present the disconnecting leader election algorithm. To do so, we will need to introduce the notion of strictly convex and erodible nodes, SCE nodes. Then, we define an erosion process in which all particles start as leader candidates, and particles that occupy SCE nodes are iteratively removed from the set of leader candidates. This process gives a leader election algorithm on shapes without holes. After which, we generalize this erosion process to shapes with holes. To conclude this part, we will sketch the correctness and linear runtime proofs of the algorithm. In the second part, we will briefly highlight the reconnecting algorithm's main ideas. Let us first go through some preliminaries. A shape is said to be simply connected if it is both connected and has no holes. In the figure to the right, the shape which is composed of all the black nodes is simply connected. For the next definitions, however, let us consider a shape with a hole. That shape's outer boundary is the set of nodes which are adjacent to its outside. Here, all of that shape's nodes are on its outer boundary. A node is said to be erodible if it is on the outer boundary and if it can be removed without disconnecting its one-hop neighborhood in the shape. In this figure, the blue-colored nodes are erodible, whereas the green ones are not. A node on the outer boundary is said to be strictly convex if it has 3 or more consecutive adjacent empty nodes outside the shape. Informally, that means if it looks pointy. The half-orange nodes are strictly convex, whereas the half-gray nodes are not. The orange and blue-colored nodes are SCE nodes. Let us now define an erosion process that elects a leader in shapes without holes. This algorithm is actually very similar to that in a paper by Di Luna, Flocchini, Santoro, Viglietta, and Yamauchi from 2017. A node is said to be eligible if it can host a leader. All occupied nodes start eligible, and the set of eligible nodes at time t is denoted by SET. By abuse of notation, SET also refers to the shape of eligible nodes, that is, the subgraph induced by the eligible nodes. We illustrate the algorithm with an execution on the following shape without holes, which you can see in the figure on the right. The scheduler first activates this particle on the bottom left. Since this particle occupies an SCE node V in the eligible shape of black nodes, then that node V becomes ineligible, it becomes yellow, and V is removed from the shape of eligible nodes, so the black nodes. Now, the second particle to be activated also occupies an SCE node when you only take the black nodes, so this occupied node becomes ineligible. And the same is true for the third activated particle. However, the fourth particle to be activated does not occupy an SCE node, and thus nothing happens. The remaining activated particles will actually occupy SCE nodes, make them ineligible, and that keeps going in this execution until the particle which occupies the last eligible node is activated and it becomes the leader. Now, this algorithm's correctness is quite straightforward. The lemma 1 here states that if the shape of eligible nodes is simply connected, then there must exist an SCE node in that shape. Lemma 2 states that if you remove that node from the shape, then the newly obtained shape is still simply connected. Since initially the shape of eligible nodes is simply connected, then you can just keep applying lemma 1 and lemma 2 iteratively to show that the algorithm removes SCE nodes until a single eligible node remains, after which a leader is elected. However, this nice erosion-based algorithm breaks if the initial shape has holes. Let us illustrate that using the following execution on the figure in the right. The first activated particle occupies an SCE node, and that node becomes ineligible. The same goes for the second activated particle. However, the third activated particle does not occupy an SCE node, and hence the algorithm does nothing. Since all remaining particles now occupy non-SCE nodes, no leader is ever elected. So this leader election algorithm does not work when the shape is initially not simply connected. In this work, we show how one can generalize this erosion process to shapes with holes so that are not simply connected. Since this process may disconnect the particle system, our algorithm only solves disconnecting leader election. In this algorithm, both occupied nodes and hole nodes are initially eligible. This ensures that the initial shape of eligible nodes is always simply connected. However, this raises some difficulties because obviously hole nodes are not occupied initially. To deal with these issues, we generalize the previous algorithm. Let us illustrate the differences with an execution on this shape with a hole. The first activated particle occupies an SCE node, which becomes ineligible. The second activated particle also occupies an SCE node. Note that in the previous algorithm this node was not SCE, but here it is since the whole node is eligible. So this node becomes ineligible and the particle expands into the adjacent whole node. Then the third activated particle occupies an SCE node and it becomes ineligible. The expanded particle is activated and contracts. The rest of the execution is the same as that of the previous algorithm. Particles which are activated here occupy SCE nodes, which are removed until finally the particle which occupies the last eligible node is activated and it becomes the leader. Note that the particle which occupies the bottom left node is disconnected from the rest of the particle system. Indeed, when the expanded particle contracts, it does not try to keep the particle system connected. This is done for efficiency reasons. This algorithm's correctness mostly follows from that of the previous algorithm, which you can see the proof on the left. Indeed, this new algorithm emulates the previous one on this new eligible shape. However, the eligible shape is composed of whole nodes, which raises some issues. In particular, how does one make sure whole nodes become ineligible? Informally, during the algorithm, particles move from the outside inwards and occupy whole nodes. When that happens, they can make these whole nodes ineligible before moving inwards again if necessary. The correctness proof can provide the O of n squared runtime up above. Indeed, the previous lemmas can easily be adapted to a node becomes ineligible every O of 1 rounds. Since the number of eligible nodes is initially bounded by O of n squared and cannot increase, the runtime follows. However, this analysis is very sequential. One considers that there are at most a constant number of SCE nodes at a time. When we look more closely at the algorithm, we see that this is not true. Instead, we get informally that the SCE-ness, the property of being SCE, propagates faster throughout the shape. The following execution, shown using the right figure, illustrates that. In this figure, the red node is the leader's occupied node, and the blue nodes are SCE nodes. The first layer consists of all nodes at distance 1 from the leader, the second layer of those at distance 2, and so on. Now, this SCE node at the bottom right is removed by the algorithm in O of 1 rounds, and it creates two new SCE nodes on this fourth layer. These nodes are also removed within an additional O of 1 round, and when that happens, you have two new SCE nodes on the fourth layer, as well as a new SCE node on the third layer. And we can see here that the SCE-ness propagates throughout the outer layer as well as into the inner layers. Informally, the main lemma of this runtime proof states that the SCE-ness propagates O of 1 distance in O of 1 rounds. Since there are at most O of diameter layers, which each have O of diameter size, because of the grid's geometry, the runtime is O of diameter rounds. For more details about this proof, you can just look at the paper. Unfortunately, the trade-off for algorithm DLE's efficient runtime is that the particle system may become disconnected. However, the terminal configurations of this disconnecting leader election algorithm are somewhat good configurations, and this is captured by the breadcrumbs lemma. Let D be the distance from the leader to the furthest occupied node when the algorithm terminates. Then, the lemma states that for any distance I, there exists a contracted particle at grid distance I from the leader. Clearly, this lemma makes it possible for the leader to reconnect the whole particle system. The following briefly explains how one can do this reconnection efficiently. The leader particle, which is the only initially collected particle, collects the other particles in phases. Whenever particles are collected, they are actually reconnected with the leader's connected component. First, the leader particle collects its neighbors, those at distance 1, and this doubles the number of collected particles. Hence, the bigger amount of collected particles can allow to search a larger area efficiently, an area which is actually double in radius. After this area is searched, then either the number of particles increases or no particle is collected. In the first case, the number of particles doubles or increases to at most n by the breadcrumbs lemma. In the second case, the algorithm terminates and all particles have been collected, once again by the breadcrumbs lemma. If you are more interested in the details behind this algorithm, please look at the paper. In summary, we provide the first deterministic linear time leader election algorithm for shaped waveforms. At the same time, we close the gap between deterministic and randomized algorithms. However, do note that our deterministic algorithms require particles to move, unlike the randomized algorithms. Finally, our result provides interesting insight into the strength of temporary long-range disconnections of the particle system. A natural future research direction is to study whether such disconnection can be useful for other problems. A second nice research direction is to consider the Amoeba model in 3D dimensions. This was mentioned in the survey paper by David, Hinanta, Richa, and Scheidler from 2019. A concrete example would be to improve leader election in that 3D setting. Thank you for listening to this talk on leader election in Programmable Matter.